So I'm going to start off by saying I'm not the best person to describe green chemistry, but it is an active area of research within the entire chemical field, and it has some really important kind of aspects behind it. So what we see up here on the slides are 12 principles that drive the green chemistry field or area of expertise. And the reason we're going to kind of talk about these is that most of chemistry has focused largely on results and not on safety. Okay? And this is why chemists have been famously involved with a lot of kind of bad discoveries. I think there was a documentary about Dow Chemicals on Netflix. There's cancer drugs, or not cancer drugs, but Aaron Brockovich with chromium in the water. Chemists have kind of historically put aside both personal safety and the safety of the community to drive forward towards new knowledge. And that's not a really good thing to be doing. So when we think about the reactions that we run, we need to be cognizant of the safety hazards that follow with them. And so a lot of what green chemistry is doing is trying to come up with ways to minimize risk, both to the individual studying and to the community that is around those chemists. Chemists should be part of the community and not excluded from it. And that's where these kind of tenets come in. So you should go through and review these. If you just look up green chemistry as a Google search, you'll see these things pop up within the American Chemical Society, or ACS. So it's an active area of research. There are lots of groups around the world focused on different parts of this process and how to improve chemistry as a field by looking at these. Okay? And so the reason why I bring it up now is at the tail end of this chapter, we talk about protecting groups. Right? And so protecting groups are kind of a weird class. And so there's two things that I want to address with them before we dig into them too much. One, first and foremost, protecting groups are kind of frowned upon, at least in modern chemistry. The point of a protecting group is to put something on the structure to prevent it from reacting, do something else, and then remove that protecting group. Which means you're trying to do one thing, but you can't do it because something else is in the way. So what you do is you do two more things, so a total of three things to do one. That's not efficient, right? And that's not a very elegant design from a chemical standpoint. If we think back to the green chemistry, atom economy is crap. You're running this 3 times as opposed to once. Okay, hazards, 3 times the chemicals. Okay, you're using more solvents. It's more energy. It's more cost because you have to pay someone to run those 3 reactions. If you designed it better, you could do it in one. Right? And so that's kind of the intent. So protecting groups are important, but they're kind of like a last resort. You don't want to be jumping out into protecting groups. The second reason why I kind of waver on talking too much about protecting groups is that in a lot of cases, the group that you use is going to be dictated based off of the rest of the functionality of your structure, which means you need a different protecting group, not for every system, but there's a sizable amount of protecting groups out there to minimize some of those secondary reactions, right? Because there's so many of them, it becomes very hard to memorize all of the protecting groups. So I think it's a bit absurd of me to make you memorize these tables of protecting groups, and instead I would rather you focus on what they do, okay, why they could be used, and then also why we should avoid using them as much as possible. So overarching picture is now shown through these slides. what we're looking at is this overall reaction here. Okay. Labile just means that there's another functionality and that group can do something. It can move around, it could come off, it can run side reactions, it can do a variety of things. So what I'm trying to do is take A and I want it to become B. The problem is that this labile group prevents that reaction from having with or occurring with any real efficiency. So what I can do is take that labile group and I can run a protection. That protection changes the chemistry of the labile group enough where it now doesn't do any side reactions. Now I can do my conversion of A to B, and then the next big part of our protection group is that we have to then undo the protection. Okay? So again, if we look at it, there's one desired reaction. Okay? That desired reaction is inhibited by something else in the structure, another functional group. So we do a reaction to get rid of that reactivity, do the one I want, and then undo the first thing I did. Okay? And there are cases where, yeah, you need to do that just because you're stuck with that many functional groups. But the idea behind kind of green chemistry is, can you come up with an alternate synthesis where that labile group isn't there yet, okay? Or that you don't have to protect it, okay? Can you change your desired reaction to ensure that that happens without affecting the labile group? Okay, so it's those kind of thoughts that you should be thinking about when looking at a synthesis in the real world. In a synthesis in this class, we'll see a couple cases of protecting groups and how they would be used to allow a reaction to occur. But again, focus on kind of the intent of what they're supposed to do and why we shouldn't be doing them. Okay? So we already talked about or presented one of these right there in the middle, highlighted in red. That's an acetal. The acetal is a highly reversible reaction. So if I'm trying to get A to become B, that carbonyl has a lot of chemistry associated with it that could potentially get in the way. So what I will go through and do is convert it into an acetal. Once in the acetal state, I no longer have that same electrophilic chemistry as the carbonyl. I could now theoretically do my conversion from A to B, and then I can remove the acetal by adding water and an acid. Okay? So this is an incredibly common protecting group for carbonyls, is forming that acetal. Okay? And cool. Efficiency-wise, I ran 2 reactions that I didn't need to. I added a bunch of chemicals in each of those cases that I didn't need to. Okay? So it's not an efficient process. Okay? If we looked at a potential example here, looking for a retrosynthesis, how could I potentially run this reaction? Okay? So let's process through the information we've got. Okay? What information do we know is present? Okay, well, we know we start with this structure. So what we should try and do is find a 5-carbon chain. Well, there's a 5-carbon chain. Interestingly enough, it also already has a bond to an oxygen. Sweet. Okay? That then means that this piece has to be added to this reaction. Okay, well, what charge do I want to have that piece have? Well, let's take a look at the red piece. Okay? So we know that one exists, so we're looking at that carbon. That carbon is partially positive because of that electrophilic carbonyl, okay? Which means to get that bond to form, I need that ring to have a negative charge. Okay, I could get the negative charge from a Grignard reagent. Okay, that negative could then go through an attack and set me up darn close, because when it attacks, pops up, we'd get the negative charge. So I could do the Grignard. We'll call it Grignard. And then H3O plus. depending on the question, maybe we need a little bit more information. How do we make the Grignard? Well, the Grignard would be made starting with the bromide. We react that bromide with the magnesium. Now we've got the Grignard. And now the Grignard could react with that to make our final product, right? So that kind of makes sense. But I intentionally left something floating off the structure, right? That piece is still here. That piece still needs to be present. And now why is that a problem? Right? Well, the Grignard is a strong nucleophile. It reacts with the electrophilic carbon up here. But isn't that also electrophilic? Well, yeah, it is. Right? And if we go all the way back to the Grignard lecture, this reagent might even show up as one of the bad ones that we can't use that as a Grignard. Okay, so we have to come up with some way that we can still get that piece into this reaction. Okay, and this is where the protecting group can come in. Instead of going straight to MgBr, whoops, I didn't want to erase all of that. I want to make sure that that carbonyl isn't present. So what I could do, whoops, is I could protect it. Let's go orange. So now when I get here, I don't have that carbonyl. And if that carbonyl is not present, the Grignard can't attack it. Okay? When I do the H3O+, the H3O+ will actually not only protonate the alcohol, but it will also revert the carbonyl, okay? Or revert my acetal back to the carbonyl. So how did I get, whoops, how did I get that structure? Well, again, I have to think backwards. That had to come from our bromine with our carbonyl on it now. To go this direction, I had to add the ethylene glycol. CH2, CH2, OH. Okay? So the protecting group is being used to kind of take away some of that chemistry so that the Grignard reaction is allowed to run. Okay? And that's the point of our protecting groups, is to allow us, because there's secondary chemistries in there. Okay? When we look at a lot of our reactions, most of them are very simple. We have one functional group. The more advanced you get, you have more and more functional groups. So you have to be a little bit more careful about your placement of your reagents in a synthesis to ensure that you're getting the reaction to happen the way you want it to, and not the way the chemistry is going to fall out. Okay? So, protection of alcohols. We just protected carbonyls. We could also protect alcohols. They're weakly acidic. They're prone to elimination. Okay? They're also prone to oxidation, which we saw in that oxidation video. So we need something to potentially protect an alcohol. Okay? So this could be done, same idea, by converting it to a different functional group that's less active. Ethers are very less active. Same deal with acetals. Okay? So what we would do is say, okay, I need a protecting group for an alcohol, and I would pull up a table or a list of reagents for protecting groups for alcohols and be like, okay, would this one work? How do I know if it would work? Well, I would have to go through and evaluate the reagents being used. Okay? Let's say I had a carboxylic acid in my structure. Well, these first two aren't going to be great protecting groups. Right? Because the very first thing that they throw in there is a base. The base is going to react with the carboxylic acid. Right? That's going to mess things up. Okay? But if I go through and look at the last one is actually under acidic conditions. If there was a carboxylic acid in my structure, the acid's not going to do anything to it. Okay? I could thereby protect the alcohol and not have to worry about that acid secondary chemistry. So our protecting groups are a lot about kind of just modifying what stuff is there versus what stuff I have. So it's a lot of looking things up and sitting down and being like, yes, this will work for the synthesis I'm trying to do. Okay? That's why I say you should look it up. Right? It's not just I've got these things memorized. Okay? There's more. You'll note that these get all sorts of different complexities associated with them. Super common one, and in my former research group, was looking at that TBDMS, right, as a protecting group for a lot of the alcohols, because we needed to protect an alcohol so that it didn't react, so I could react to different things. Then we'd remove the protecting group so we could do over there and we could continue things out. Right? So depending on what you're trying to do, you're going to change the reagent. Okay? Note also, it's not just the reagent to get the protecting group on. I also have to be aware about the deprotection step. What reagents, whoops, that's an eraser, what reagents are getting used in each of those cases? Because if those reagents could run side reactions, that becomes problematic as well. Okay? So we're looking at both of those pieces in the grand scheme of our huge structure. Right? Most of the syntheses we deal with are relatively small, so we don't really have to get exposed much to this protecting group process and really practicing it. What I want you to do is be aware that it's there and that you can look these things up. This is why there's a few questions on it in the smart work, but what I'm expecting is that you look these things up. Okay? Is that really the last slide? Oh, wow, look at that. The last thing I'll point out before we go ahead and end this is that synthesis, you will see things like DHP, you'll see things like TFOH, MSOH, okay? I don't expect you to know what those abbreviations are. When it comes to an exam, what I will do is give you the abbreviation and the structure so that you can interpret it from the structure. Or if you've memorized, you can interpret it from the formula that you've memorized. So I give you both paths, and I really try hard to ensure that depending on which path you're trying to negotiate this class, memorize and get the hell out versus really understand and apply it, you have the ability to do both for an individual question. Okay. In the homework, it's going to be everything because I know you have access to a textbook. With the exams, it's a little bit more questionable, and I don't expect you to be looking things up. What I expect you to be doing is thinking through the chemistry that's there. Okay. With that, we have covered all of Unit 2. Thank you for listening, and I wish you the best of luck on Exam 2.